Okay, hi everyone. I guess the issues are resolved now. Um, uh, Today I want to continue talking about groups, and I hope that now that Carlos is around, we will get to have a bit more discussion. So I remind you, questions are not only welcome, they are essential for these sessions to be complete. And last time I got the feeling that you didn't get, or some people didn't get the definitions of kernel and image right. So let me revise it. So if we have a group map, this is my shortened terminology to homomorphism. Then we can define the image of F to be the set of, okay, you can write it in different ways. Let's say the set of all Y in H such that there exists X in G for which F of X is equal to Y. But you can also write it for short as Fx X in G. So you can think of image F as the collection of all possible outputs when you input any element in G. And the kernel, so of course, the image of F is a subset of H, and we saw last time that it is in fact a subgroup of H. And kind of dually, the kernel of F is the set of all X in G such that F of X is equal to E. And here, of course, the E, I suppress the index of E by the group because it should be understood from the context that E is the neutral element of H. And of course, the kernel of F is a subset of G, and we saw, in fact, that it is a subgroup. And the picture is as follows. Here you have G and H. And let's say you have the neutral element here, E, here, E. Then the collection of all elements in G that go to E, this is the kernel. And the image is what happens if you take, sorry, if you take all the possible elements in G and apply F on them. So this thing in red is the image of F. And notice F is surjective if and only if the image of F is the whole group H. This is actually true for any function. You don't need F to be a homomorphism. The image of F is defined for any function from a set G to a set H, and the image of F is equal to the target set if and only if the function is surjective. And dually, F is injective if and only if kernel of F is the trivial subgroup. This requires a bit justification because it does use the fact that F is a homomorphism. But how do we see this? So if the kernel of F is E, and well, maybe the easier direction, if F is injective, then clearly the kernel of F cannot contain anything else than E, because otherwise it would mean that two elements, E and some non-unit element in G, are mapped to E. So this would contradict the injectiveness. Conversely, if kernel of F is E, and you have two elements, let's say X and X prime in G are such that F of X is equal to F of X prime, then F is a homomorphism. So what I can do, this is equivalent to say that F X prime times F X minus 1 is equal to E. I just multiply the equation by Fx inverse. And since F is a homomorphism, it commutes with the binary operation and with taking inverses. So I get that F of X prime X minus 1 is equal to E, which is the same as saying that X prime times X minus 1 is an element in the kernel. But the kernel we assume to be trivial. So this implies, or in fact equivalent, to say that X prime X minus 1 is equal to E. And this is, of course, equivalent to say that X prime is equal to X. So F is indeed injective. And to give you maybe a toy example, you take F from integers modulo 5 to integers modulo 10. Given by F of X is equal to 2x modulo 10. This function, it's very easy to see that it's a homomorphism. Because if you take x and y in integers modulo 5, and you add them together, and then you apply f, well, here the add should be addition modulo 5. But this is by definition 2 of x plus y modulo 10. And by basic properties of modulus, this is equal to 2x modulo 10 plus 2y modulo 10, which is simply f of x plus f of y. So the fact that I have the equality between the two parallel expressions means that I have a group map. And let's see what is the image of f. Can anybody say?
Could be all of the integers modulo 10, no?
Well, is every integer modulo 10 of the form 2x?
Oh no, I see. So it's just half of it.
But which half?
The even one?
Exactly. So this is the set of 0, 2, 4, 8. Sorry, 6 is missing. Okay, what is the kernel of f? Anybody? I mean, it's yes.
I don't see. No, sorry, I was gonna say I don't see any hands raised, but anyone can just jump and talk if they want to. Like, if there's no restrictions or anything.
Is it 0 and 5?
Exactly. Okay. Well, it's 5 is equal to 0 in Z modulo 5, so it's just 0. Right?
Ah, yeah.
So, so we know that f is injective. And of course, it is going to be surjective on its image. I mean, the image of f is a subgroup of the target group. So it's a subgroup of Z modulo 10. And as I said earlier, any subgroup is a group in its own right. I mean, because it means that it's if you restrict the binary operation from the ambient group to the subgroup, you have all the axioms of the group satisfied. So you could view image f as simply as a group in its own right. And so of course you could say f goes instead to Z mod 10, it goes to image f. That's also a legitimate writing. Of course, I'm abusing the notation a bit. It's formally speaking, it's not f because it has a different target set, but it's really the same. And now this map, this maybe we call it F bar. F bar is injective because F was injective. Plus, it's surjective because any function is going to be surjective onto its image. So plus, of course, it's also a group map. So we get that F bar, or rather integers modulo 5, is isomorphic to image of F. Because F bar is such an isomorphism. But in fact, you don't have to have these fancy considerations. You can just look at the multiplication table. I mean, 0, 1, 2, 3, 4. And here the multiplication is really addition modulo 5. So I write it like this, plus mod 5. And here I have 0, 2, 4, 6, 8, 0, 2, 4, 6, 8, and the operation is addition modulo 10. But notice that I simply, from here to here, I blew up all the multiplication table by 2. I mean, I blew up all the numbers and I blew up the modulus. So if I feed this multiplication table to a computer, it's the same. I mean, here I have a list of symbols, but when I check what is the multiplication of this list of symbols, it's the same. So this is why, at least from an elementary point of view, the two groups here are isomorphic. Okay, and what we saw last time if I take a group map from G to H, then of course I can look at the image of F, but G is not going to be isomorphic to the image of F. However, if you divide by the kernel, then you get such an isomorphism. And the intuitive explanation for this is that kernel of F is kind of a measurement for how close F is to be an injective map. And so, of course, F is going to be surjective onto its image. And it might not be injective, but since kernel F measures how much F is not injective, once you mod out by the kernel, you get an injective map. So then by this, you get an injective plus surjective map, which is an isomorphism. Any questions?
Doesn't look like there's any so far.
Yeah, I see something in the chat.
Oh,
The structure of a group modulo the kernel of some homomorphism F has the same structure as the image of F. Well, yes, this is what the theorem says. This was a theorem, I remind you. And if you think of it, you can, I mean, there is a certain duality between injective and surjective maps. Yes, is there a question? So what I'm saying, there is a certain duality between injective and surjective map. I don't want to put it in formal terms because I think it is a bit too advanced for us now. But just intuitively speaking, if you could extend the duality between injective and surjective maps to a kernel and image. I mean, because a map is surjective if and only if the image of this map is the entire group age, and it is injective if and only if the kernel of this map is minimal. I mean, the trivial subgroup in G. So this kind of duality is expressed in this isomorphism theorem. Okay, so we are going to talk a lot about finite abelian groups. And when you consider finite groups in general, there is a very natural notion. So let G be a group, and G an element in this group capital G. The order of G, denoted O of G, is the minimal positive integer n such that G to the n is equal to E. I guess the minimal non-negative integer because it could be 0. Well, sorry. And if no such number exists, we set O of G to be infinity. Now, if G is finite, then the order of any element in G has to be finite, because you get you take the powers of G. At some point, you have to get elements that you already expressed in lower powers because G is finite. So at some point, G to the n must be equal to E. And what we want to do is to kind of, for finite groups, we would like to decompose the group into sort of clusters of elements of the same order. So for this, we're going to do a little bit of like elementary number theory. So let me remind you. If m and n are natural numbers, the least common divisor this is denoted as LCM of m and n. It is the minimal number natural number L such that m divides L and n divides L. Now, you know that every integer can be decomposed into a product of powers of primes. If we have two integers,
sorry, Maitan, can you
yes,
give more intuition on that? Like how you can form every single integer just multiplying primes?
Well, okay. So, you take an integer, in our case, m, and you look for all the primes, let's call it this fancy P.
I see. I did some maths in my head and I saw it now. Okay. But is this is this proven somehow mathematically?
Yes, I mean, you take the definition. First of all, in the notes, there is a section called elementary number theory. So you can look at it there. But it's very simple. I mean, let's take PM is all the primes that are smaller or equal to M. And what you do is you look out of PM which are the primes that divide M. And once they divide let's say if P divides M, then you can then consider the set of all primes that are smaller or equal to M modulo P.
Okay, that makes sense.
And by this inductive process, you will express M as a product of primes, but there could be some repetition. So so I write it like this: S1, P1 to the S1, up to PK to the SK. Right? This means that where P1 up to PK are primes. Okay, and if I want to be concise, then S1 up to SK are some some integers which are bigger or equal to 1. But if I have two integers, m and n, I can take the prime decomposition of m and n over the same set of primes. So I write it like this: pk here tk t1, where si and ti are now allowed to be also 0. So this is by, I just take, I mean, the prime decomposition of m and n could consist of different primes. But if I want to kind of look at m and n on the same level, then I add artificially all the primes that appear in the factorization of m and n. This is the list of my primes, p1 up to pk. And I allow the powers to be possibly 0. So then I could write m as the product of powers of the pi's, and n of the product of the power of the pi's, where only the exponents may be different, but the number of primes and in the decomposition, or the set of prime in the decomposition, is the same. So if you do this, then you can neatly express LCM of m and n as simply as you take the product of primes, and in each exponent you take the minimum. Is this clear?
Yep.
Okay, so this is a nice trick, and now we come to another famous theorem. This is Cauchy. If G is a finite abelian group, and P a prime such that P divides the order of the group G, then there exists G in G with order exactly P. And I remind you, order exactly P means that G to the power of P is equal to E. Okay, so just in terms of the statement, you can view it as kind of a partial converse to Lagrange theorem. Lagrange tells you that if you have a subgroup of G, then the order of the subgroup divides the order of the ambient group G. And Cauchy theorem, I mean, you could ask, okay, so suppose I have a number that divides the order of the group G. Do I actually have a subgroup of this order? Well, so Cauchy tells you something similar. We will soon see that you can really construct a subgroup of order G, but of order P. in such a case, but for now, it simply gives you an element of order P. Okay, so assume by contradiction that there doesn't exist G in G with order P. If this is true, then there is no element in G of order divisible by P. And why is that? If there was, if G to the R is equal to E, and P divides R, then I can take G to the R divided by P. If you raise it to the P power, you simply get G to the R, which is assumed to be E. And this is a contradiction because we assume that there is no element of order P. So let G1 up to Gn be some enumeration of the elements of G, and let Gi or rather Mi be the order of Gi. Right? Each of the GIs has some order. So of course, for any I, P cannot divide the order of Gi. Let M be the LCM of all the M's, all the MIs, equals 1 up to N. Then P cannot divide N, cannot divide M, because P does not divide each of the MIs. And when you take M, you simply take the minimum power in the prime decomposition if you look at it in the way we talked before. So if P was some factor in this product, it would mean that P would be a factor in some product expressing one of the MIs, and that would mean that P divides MI, which we know that is cannot happen. So P cannot divide M. And furthermore, Gi to the M, it must be equal to E, because, well, Gi to the M, I mean, M divides Mi divides M. So Gi to the M has to be the unit element. Now, for a natural number n, I write G to the minus n to be G to the minus 1 to the power of n. Then we can define a map f from integers modulo m times itself n times to G. And this goes as a f of a1 up to an is going to be equal to G1 to the a1 up to Gn to the an. And I claim that F is a group map. Well, how do we check that F is a group map? Recall that in the Cartesian product, the binary operation is done coordinate-wise. And in integers modulo m, the binary operation is addition modulo m. In G, the operation, because we don't assume anything on G, the convention is that the operation is multiplication. So what I need to check is that if I take A1 up to AN plus B1 up to Bn, I get f of A1 up to AN multiplied by f of B1 up to Bn. But let's expand this left-hand side. Well, what is addition of these two elements? We said that addition we do addition coordinate-wise modulo m. So I can write it as f of a1 plus b1 up to an plus bn. But of course, this is equal to g of a1 plus b1. Sorry, g1 up to gn to the an plus bn. And since G, so this I can decompose, of course, to G1 to the A1, G1 to the B1, up to Gn to the An, Gn to the Bn. And since G is a billion, I can commute. I can commute all these all the factors of this product to get f of A1 up to An multiplied by f of B1 up to Bn. So what I get is the question mark here is indeed true. And I got a group homomorphism as in the blue box. Any questions about this step?
Not from my side. I don't see anything in the chat.
Okay, so once we have this homomorphism, note F is clearly surjective. Well, how do I know? I want a source for GI. So I take simply the sequence 0 and here 1. This is in the ith place. This is, of course, is going to be, by the definition of F, is going to be GI, or GI to the 1. So I have a source, and G1 up to Gn is the full enumeration of G. So F is surjective. Now, by the first isomorphism theorem, I get that Zm to the n. This is my shortened notation for the n-fold Cartesian product of Zm with itself, divided by the kernel of F, is going to be isomorphic to the image of F, but the image of F is everything since F is surjective. So this is going to be isomorphic to G. By Lagrange.
So Metal, like, I don't see why is it so subjective. Like, if you, just because you have all of these zeros and the identity at the if place and you get G of GI, why does this imply that it's subjective?
Well, remember, F is something that maps into G, and G, we took an enumeration G1 up to Gn. This is a full enumeration of G.
Sure.
So what do I need to show you in order to prove that F is surjective? I need to show that for any possible output GI, there exists an input in the source, I mean in Zm to the power of n, such that the program maps this input to this output. So
okay, I see.
Okay.
So you just need to prove that you can go from the domain to the image, and you can derive to any of the images of the function or the application.
I mean, this I prove that the image of F is all of G.
Makes sense. Okay. Makes sense. I see now. I see. I thought that it had something to do with the fact that you can multiple items in the domain can go to the same image, but this property doesn't matter at all. You just wanted to prove that the image of F is G. That's all. That was
Yeah.
Okay, fair enough.
So by the first isomorphism theorem, I get isomorphism of groups Zm to the n modulo the kernel is isomorphic to the image, but the image of F is all of G. So it's isomorphic to G.
Okay, makes sense.
Now, by Lagrange, the number of elements in the kernel times the number of elements in G must be equal to the number of elements in Zm to the n. Right? I mean, kernel of F is a subgroup of Zm to the n, so it must divide Zm. I mean, the order of the kernel must divide Zm to the n. I mean, is of course m to the n. But Lagrange theorem tells you really this equation, because it tells you that the number of elements in this group is the number of distinct cosets. So, or the number of elements in these groups is the number of distinct cosets. So this really means that you get an equation like this. Okay, we're almost done. So now I conclude that the number of elements in G must divide m to the n. But P divides the number of elements in G by assumption. And P does not divide M. So P does not divide also M to the N, and that's a contradiction. Any questions about the theorem?
Sorry, just to recall, this is a contradiction to what proposition again?
So we assume that there is no element of order P.
Ah, okay.
I mean, the statement of the theorem says that there must be an element of order P. I mean, we assume that P divides the order of the group, and the statement is that, I mean, there is an element of order P. So I assume by contradiction that there is no such.
Okay, yeah, got it. Makes sense.
Other questions? So I think now would be a good time to break. Let's meet here in 10 past 11 or 10 minutes from now.
Sure. Today we will need to finish at 12, at least recording wise. Because I have another meeting. So, I mean, I hope it's not an issue, but yeah, I will talk the recording at least. So either you can do a review or we can just miss a part of the recording, whatever you want.
Okay.
Sure. See you.
Okay. See you soon.
See you in 10 minutes. Okay, let's go.
Okay, so I just want to make a correction. I called the LCM the least common divisor, I think, but of course it should be least common multiplier. Here, this should be the least common multiplier. I mean, it's the minimal number such that both integers m and n divide the number. So of course, m times n is such a number, but there possibly there could be a smaller number that has this property. Any questions about Cauchy theorem?
There's a question in the chat.
So in the case of an elliptic curve, which is an abelian group, when we prove a homomorphism between the points on the elliptic curve E and the points in one of the prime order subgroups, this would show we are squeezing the structure of E into the prime order subgroup formed by this generator. Well, okay, we didn't talk about generators, so I will leave the last part of the question open. But what is happening in elliptic curves is that you take the collection of all solution to the equation of the elliptic curve over the prime field. This is the order of this is something like P. It could be slightly bigger, it could be slightly smaller. This is a result called Hasse or Hasse-Weil theorem. And then assuming that this is if Q a prime such that Q divides the order of the elliptic curve, then by Cauchy, it tells you that there exists an element, let's call it, we usually denote the elements of an elliptic curve by capital letters, because they are like points. And elliptic curve is an abelian group and denoted with additive notation. So Cauchy theorem in this case would tell you that there exists a number, an element in a point on the elliptic curve such that P plus P with itself Q times is equal to the zero element. And this is, of course, this is denoted as QP. And generally speaking, if G is an element in G of order n, then well, I can consider, let's call it H, to be the set of all positive powers of G. So I have E, which is G to the 0. Then I have G, and up to G to the n minus 1, because G to the n is going to be the neutral element again. And in this set, in this description of the set, all the elements are distinct. If K, and say strictly smaller than n, then GK cannot be equal to GL, because otherwise GL minus K would be equal to E, and this is so the order of G would be smaller or equal to L minus K, which is strictly smaller than N. So, and this is all to say that if you have an element of order G, of order N, then you can look at the set of all positive or non-negative powers of G, of this element, and you get a set of size n, right? You have from 0 up to n minus 1. And moreover, so H is a subgroup of G. Well, of course, it has the neutral element. If you multiply two non-negative powers of G, you get, again, a non-negative power of G. You take modulo n, then you land in this set again. And just to check the inverse, so what is the inverse of G to the K? This is going to be G to the n minus K. Right? Because if you multiply G to the n minus K and G to the K, you get G to the n, which is by assumption the neutral element E. So this is all to say that if in this case of the elliptic curve with a point P of order Q, we get this H is denoted as this square, triangular brackets G. This is like the collection of all powers of G. So in the case of an elliptic curve, you measure the number of points. This can be computed by several algorithms. You take a prime Q that divides the order of the group E of FP, and Cauchy tells you that there is an element P of order Q, and this would imply that you get a group generated by P. I mean, you take all the positive powers or non-negative powers of P, and you get a subgroup of E FP, and this subgroup is of order Q. And this, in fact, well, okay. So is this answering the question? QB?
Sorry, shouldn't it be P to the power of Q instead of Q to the power of P?
You mean here?
Yeah.
Here, this is in additive notation. I mean, of course, in multiplicative notation, I would write P to the power of Q. Of Q. This would mean P times P times P, Q times. But in additive notation, I write QP.
Ah, okay, got it. Yeah.
Okay, to mean P plus P plus P, Q times.
I have a question.
Yes.
So what you basically say, if the order if the number of elements in an elliptic curve group has a prime which divides it, then there exists a subgroup with that size, right?
More than that, the subgroup is generated by one element. Yes.
So we have a cyclic subgroup.
Yes.
Is that something which generally holds, or I mean?
Yeah, I mean, Cauchy theorem, it does not depend on any elliptic curve structure. It's a general statement about groups.
Yeah, but isn't it? So does Cauchy say that there exists a subgroup, or does it say a set?
That's the content of what I was trying to say here generally. I mean, because if you have G in G of order n, I mean, Cauchy theorem tells you that in particular, if P divides the order of the group, then you get some element of order P. Okay, but here I'm saying generally for any integer n, if you have an element of order n, then you get a subgroup by taking all the powers of this element. I mean, all the positive powers.
Okay, I see.
You see, I mean, why is it so? First, I mean, why is it a subgroup? It contains the neutral element, of course. If you multiply GK and GL, you get GK plus L. Possibly K plus L is bigger than N, but then GK plus G to the K plus L is going to be G to the K plus L modulo N, right?
Yeah.
I mean, it's going to be G to the N times some. Okay, so this set is closed under multiplication, and moreover, every element has an inverse. Why? Because if you take a G to the K, then G to the N minus K is going to be the inverse. I mean, if you multiply G to the K and G to the N minus K, you get G to the N, which is E. So every element in this set H has an inverse. So H is in fact a subgroup. This was the
Yeah, so every group has a subgroup for for a prime factor basically. So
yes.
for the that's what okay, all right. A
Yes.
cyclic subgroup, in fact.
Yes.
Okay.
So this you can regard it as a partial converse to Lagrange. Lagrange tells you if you have a subgroup, then the order of the subgroup must divide the order of the ambient group. And Cauchy theorem says, well, okay, if you have a prime divisor of the order of the ambient group, then you must have a subgroup, in fact, a cyclic subgroup of this order.
Okay, makes sense. Thanks.
Other questions? All right. We need to have an example. So we simply recycle the examples we have. We know that Z mod 10 by Cauchy, it must have a subgroup of order 5. But in fact, we really saw we saw that 0, 2, 4, 6, 8 is indeed a subgroup of Z mod 10. And this is in fact the only subgroup. So, but that's another matter. It's the only subgroup of order 5. Okay. So we talked about cyclic groups, but I really want to put this definition formally. So let G be a group, and a G some element in capital G. The group generated by G, this is in fact in the general case, I need to define it as G to the N such that N is allowed to be any integer. Well, of course, I remind you g to the minus n is by definition g minus 1 to the n. And 2, g is called cyclic if there exists some g in g such that g is simply equal to g. Okay, and this, I didn't give it a name, this is called the group generated by G. Okay, notice the difference here. G triangular brackets is all the integer powers of G, and in this case we took all the non-negative powers of G. Can someone say why these two are equal? In the case we discussed, in the finite group case? I mean, if G is finite, then G in G must have a finite order. So the group generated by the element G, which by definition is all the powers, G to the n in Z, is simply going to be equal to E, which is G to the 0, G up to G to the n minus 1. Right? And the reason is, I mean, of course, if you take G to the n plus something plus k, this is equal to G to the k, because G to the n is equal to E. And if you take G to the minus k, then this is G to the minus 1, or it's G to the k to the power of minus 1. But we saw that G to the k inverse is in fact G to the n minus k. If you multiply two of these, you get G to the n, which is E. So in fact, in the case of a finite group, I could express the group generated by G in only the non-negative powers instead of taking powers over all integer. Is this point clear? Any questions about the definitions?
Thing is clear. There's no questions in the chat so far.
Okay, so examples. One, integers modulo n is cyclic. It is generated by 1. Right? You take 1 plus 1 plus 1 plus 1 plus 1, you get all the elements of integers modulo n. Two, the integers is also a cyclic group. You take 1, you can, I mean, to take the group generated by 1 is to take all the elements n times 1 such that n is in Z. So this is Z. But notice that I can also generate the group of integers by -1. Because I allow here n to be any integer. So this is going to be n times -1 n in Z. And that's again the entire set of integers. So this is to show you that a generator does not need to be unique. A cyclic group can be generated by different elements. Now we take a Cartesian product of two modulus. Let's say modulo 2 and modulo 3. And I claim that this is generated by the element 1, 1. Well, here we have 6 elements, so we can really do it very explicitly. Take 1, 1 and add to it 1, 1. You get 1, 2. Sorry, you get 2, 2. But 2, 2 in the first coordinate, we have modulo 2, so this is really 0, 0, 2. Then I take 1, 1 plus 1, 1 plus 1, 1. Well, I get 1, 3, but in the second coordinate, we take modulo 3, so I get 1, 0. Then I would take, I just write it like this, 1, 1 times 4. This is adding 1, 1 to itself 4 times. I would get 0, 1. And 5 times 1, 1 is going to be 1, 2. This is 3 times 1, 1. 2. So I got everything, right? Of course, I have also 1, 1, and I have 0 times 1, 1 is simply 0, 0. Okay, so I got, yes?
But this only works if they don't divide each other, right?
Okay, this will be a theorem. Yes, but for now, we just take a simple example.
Also, on the way you have defined the groups and everything, so now I don't know how to say that. Like it looks like 0 is a completely different group that it's a site because you cannot get to it unless you multiply by 0. So
yes, but when I say 0 times 1, I mean, this is a constant source of potential confusion. I mean, when I talk generally about groups, I use the multiplicative notation G dot E. Okay. And under this notation, G to the N, of course, is G operation G with itself N times.
Sure.
Now, if I use additive notation, then I usually use the 0 as instead of E. And then instead of G to the N, I write N times G.
Okay,
This is the same.
okay, I
It's
see.
basically G plus G plus G. I mean, G operation G N times. And this is what is, so when I write here 0 times 1 times 1, it really corresponds to what we called G to the 0.
Okay, makes sense.
Okay, so this is, which is always E.
Sure.
Okay. Observe. If G is cyclic, then it is abelian. I mean, if G is cyclic, then I can write G as generated by some element lowercase g, and this really means I take all the integer powers of G, and of course G to the K times G to the L is going to be equal to G to the L times G to the K. So multiplying any two elements is in G is commutative. Now I claim that for any n, for any natural number n, there exists a cyclic group of order n, and it is unique up to isomorphism. Okay, I will soon explain. I will explain during the proof what it means to be unique up to isomorphism. But for now, well, the first part of the statement you should be able to prove immediately. Anybody knows why the first part of the statement is true? So the blue part, why is the blue part true?
Because of Cauchy?
You don't need Cauchy here. All you need is a cyclic group of order n for every n. We actually saw a cyclic group of order n.
Is it because you can generate a group of order n with like 1?
Exactly. So
Sure.
I mean, Zn is cyclic. then is cyclic. I mean, the n, for example, is generated by 1. Now, if G is a cyclic group, let's say I write it like this, G equals the group generated by lowercase g, and is a cyclic group of order n. Then, of course, this we discussed earlier. I can write G as all the non-negative powers of the generator. So this is E, G, up to G to the n minus 1. And define f from, let's say, integers modulo n to g by f of k is equal to g to the k. F is a group map. Well, how do I see it? I need to show that f of k plus k prime is going to be equal to f of k multiplied by f of k prime. Because again, the operation in the domain group is plus, and the operation in the target group is multiplication. But f to the k plus k prime is simply g to the k plus k prime. And this is, of course, equal to g to the k times g to the k prime. So f is a group map. And moreover, f is clearly bijective. I mean, this is a one-to-one correspondence. I have is integers modulo n is simply all the numbers 0 up to n minus 1. And I map each of these numbers to g to the power of this number. So f is an isomorphism. Okay, and this is really the meaning of this this blue part of the the purple part of the statement, that basically any group that is cyclic of order n, it must be isomorphic to integers modulo n. So there is up to isomorphism, there is only one cyclic group of order n, and this would be integers modulo n. Any questions about the proposition? Okay, so we said that a cyclic group can be generated by more than one element. And the question now we want to ask ourselves is, how many possible generators are in integers modulo n? And this is the next proposition. an element k in integers modulo n is a generator, and when I say generator, I really mean that the group generated by k is the whole ambient group. If and only if GCD of n and k is equal to 1. Okay, GCD, the greatest common divisor, is the maximal positive integer that divides both n and k.
So this means that there's no other element in integers modulo n that divides m. So so basically, in order to be a generator, this number multiplied by itself needs to produce all of the elements of integers modulo n, right?
Not multiplied, but added, because
Added. Okay, yeah, added. Sorry, yeah, my bad.
I mean,
So that
yes, go on.
So that means there should not, if you pick, I don't know, a random number inside of integers modulo n, this is a generator if only if there's no other number within integers modulo n such that this can be divided by any of the others. Does this make sense? Like you kind of need to make sure that this
No,
doesn't fall in a subgroup or something like that. Or am I?
I think, I mean, the statement you made is close, but it's inaccurate eventually. I mean, a number is a generator if and only if it is coprime to the modulus.
Okay, fair enough. That makes sense.
This is called coprime. Coprime numbers are numbers that do not have any common divisor, well, except one, right? So you really need a number that is coprime to the modulus in order to generate everything. If you think of it just intuitively, imagine that k would not be coprime to the modulus, then it would have some common divisor that is greater than 1, and then this common divisor, once you take the power of k, well, you will get I mean, then k will have an order smaller than n.
Yep.
Okay, so if it will have an order smaller than n, it could not generate everything. But we will prove this. Okay, so you maybe you can see the proof also for clarification. Okay, so if k is a generator, I mean, actually, this is equivalent. Since we want to prove an if and only if statement, let me put it as an equivalence. K is a generator if and only if integers modulo n is equal to 0, k up to n minus 1 times k. If GCD of n and k is bigger than 1, then I can write, let's say this GCD I call gamma, then I can write n equals gamma times s, and k equals gamma times t. But then what I get is that S times K is S times gamma times T, and S times gamma is N, so this is NT, and this is 0 modulo N. But here, S and T, I mean, S is strictly smaller than N. So K cannot have order N. Right? If I found a number S that is smaller than N, such that S times K is 0 modulo N, then K must have an order that is smaller or equal to S, which is smaller than N. So this is a contradiction. I mean, so this is one direction, right? If the GCD of the K and N is bigger than 1, then K is not a generator. Conversely, if the GCD, which we call gamma, of N and K is equal to 1, we claim that the numbers 0, K, 2K, up to N minus 1, K, are all distinct. Well, otherwise, let's say that Sk is equal to Tk for some S and T smaller than N, then S minus T K equal to Nx. I mean, they are equal modulo N, right? So S minus T times K is 0 modulo N, which means it's N times X for some X. And since K does not divide N, I mean, if they have a GCD equal 1, then in particular, K cannot divide N. So it means that K must divide X. But then S minus T K, which we assume to be equal to N times X, is going to be equal to N times K times Y for some Y. So and now I can cancel out the K. S minus T is equal to Y. Sorry, is equal to 0. modulo n equal to ny, which is equal to 0 modulo n. So this shows you that the set here in the blue box is a set of n distinct elements. Okay, this, of course, this last part is a contradiction. I mean, if s minus t is n ny for some y, and s and t are strictly smaller than n, well, then s is equal to t. Okay, so this is all to say that we finished the proof. And let me make a definition, or n equals, for n a natural number, the Euler totient function is, this is denoted as phi of n. It's the number of all elements k such that k is strictly, well, is smaller or equal than n, bigger or equal to 1, and GCD of n and k is equal to 1. Okay, this is something you can find on the internet, or there is like a Sage method that computes the Euler totient function. So just in other words, using this definition, phi n is the number of, is also the number of generators of distinct generators of integers modulo n. Okay, we are almost out of time. So any questions about this last part?
All good, and it seems that there's nothing in the chat either.
All right. So let's stop here and meet next week.